Without further ado, I would like to invite back to the stage my friend, Professor Schmiegelow, for his second lecture. Please.
Hi. So, thank you for joining again for the late night sessions. Not so late. Yesterday was a bit later. So we will continue to learn how to twist, turn, and kick ions with structured light. So today we're going to get a little bit more into the detail of how structured light, as we learned yesterday, can interact with single atomic particles. And that's the illustration that somehow has been appearing near the title in every of the slides, which is this idea, which is we have some kind of atom, which is, of course, blue, as we know, and hollow beam, which in this case is fake orange. And the idea is to try and see what happens when we move this atom around this beam, what kind of interactions can we have, and how does it depend on the position of the beam, and what kind of funny things we have. So before that, there will be a little bit of a recap from yesterday. And I've been receiving a lot of questions about all the houses that we used to rent and the things that happened there. I might be able to put up a small collection of pictures, which probably won't mean anything to you people because you're not on them and you don't know the people on them, or probably you do, and they're your professors or whatever. I'll see what I can get for tomorrow. So as I said, yesterday we looked a little bit about the basic of structured light. Today we're looking at structured light and atoms. And tomorrow we're going to go into a little bit further, which is structured light and optical forces. So today is a little bit more of the interaction of structured light with the valence electron, with the inner part of the atom, and tomorrow is with the center of mass, or the whole of the atom. So a review about yesterday. So this whole thing started when we started asking ourselves what would happen if you replace an ion, which is around 60 nanometers, spread the wave packet function of a trapped ion in a harmonic trap inside a beam, which you can focus down to, if you're very good, to around the micron. And I will try to convince you today how you actually can see things, even though the atom is in the dark center of the beam. So you would probably say like, it's dark in there, what will happen? The atom will feel no forces, will feel no fields. Well, here are some things that the atom can feel. And actually, I will show you today how an atom can get excited even when it is at the center of one of these hollow beams. So what did we see? We looked at different kinds of structured light, but in particular I show you, we discussed twisted light. So twisted light is light that has an oscillatory part, a plane wave part, a polarization part, and then has a structure part. This structure part we open and has many terms, of which we identify first the Gaussian beam profile, and then some other curvature and Gouy phases and things that I didn't discuss and I won't discuss even today, some normalization constant, but then some functions which are kind of interesting. So this is rho to the L. So this rho to the L gives you the minimum at the center, which as you increase the power of L, this minimum first is linear, then it's quadratic, and so on. And then there's an extra Laguerre function, which gives you actually, it reshapes these rings that you see outside. That gives you the P and the L parts. But very interestingly, as I showed you, there's this extra azimuthal part. So this phi is the azimuthal coordinate that runs around the beam axis. And what we can calculate is that if a beam, I forgot to start my timer, that if a beam of this kind is analyzed in terms of its angular momentum, you can see that the angular momentum along the z direction, where here the z direction is the propagation direction, has two important components. One component that is proportional to L, so it's proportional to the phase, this phase information that you have here, and we will call this orbital angular momentum. And another part that is proportional to sigma z, which is the typical +1 or -1 if you have circular right or circular left polarization. and of course something that has to do with the beam intensity or beam intensity around the beam. And an image that I didn't put yesterday, but I'd like to share, is if you look at what happens where are the planes of constant phase in this beam, so for the L equal to 0, L equal to 1, L equal to 2, you see that in a plane the intensity looks like that. This is what I showed you. If you look at what happens with the phase is constant in one plane. The phase goes round 1 times 2 pi on the L equal to 1 and goes around 2 times 2 pi on the L equal to 2. That's the L to the I phase. And if you look at how the surfaces of equal phase evolve in these beams, of course, in a Gaussian beam is every lambda half you have the same constant plane, and in these beams the phase, the surfaces of equal phase are spirals. In the case of L equal to 1, it's just one spiral around the axis, and in the L equal to 2, it's 2 spirals around the axis, so you have 2 opposite parts, like here and here, or here and here, wherever you want, with the same phase. So it's like a bi-spiral, and so on and so forth for bigger L's. This structure is the reason why we somehow say photons in these beams are twirling around the axis, are rotating around the axis, and this is the way we somehow interpret and intuitively construct the idea of angular momentum of these photons. So I showed you how this angular momentum can actually rotate this particle number 4 here. We also saw some very nice impressive videos. So, and that allowed us to complete this table where we have how does light-matter interaction reveal itself in different planes. So how does matter affect light in refracting it or rotating the polarization? How the other way around, light can turn matter either by pushing it, either by rotating it because of polarization, or either rotating it because of the angular momentum. But then we have these 2 holes here, which I will address today. So one of them is the mechanical effects of light. So how can light that has angular momentum be turned by matter? And I will discuss that at the end of today. But what I will discuss first is how does it affect atomic spectroscopy? So how are the different absorption lines, and how is basically the inner part of an atom affected by the angular momentum, the orbital angular momentum of the beam? So, and to do so, I have to go a little bit into discussing a little bit light-matter interactions at the basic level, and I will get into reviewing the idea of quadrupole interactions. So, look at this beam. These beams have a very interesting thing. If you look at beam with L equal to 0, 1, and 2, and if you look at what happens at the center of this beam, so if you think about an atom like lying here, so this is the function that creates an envelope around all of this, the traveling wave and the oscillating part. So this field, of course, will be like this at some time, it will be opposite at some time, and an atom will basically, placed at the center of this field, will basically feel a field turning on, off, on, off, on, off. So it would be like, if you would be on, I always forget the name of this in English, in Spanish it's sube y baja.
Up and down.
Yeah.
Seesaw.
Seesaw, you know this child's games in the park, where you sit on one side, the other side, so seesaw. Okay. So in this case, it would be like at the end of the seesaw. You would be just going up and down and up and down and up and down. But if you think about what happens if you are in this kind of beam, although you're at the place where the field is almost null, you're at a place, it looks like if you were sitting at the middle of the seesaw, which is something which is also fun to do, and it's actually not nothing. You basically go like that and you shake somehow a little bit sideways. And I will try to convince you that in this case, atoms can also get excited in a different way, actually through quadrupole interactions. What happens here is a little bit more complicated. Actually, this is like a horse saddle seesaw. So if you look at it in one plane, it's like this, but in the plane, so this is the cut like this, but if you look at it in the other cut, it actually goes in the other direction. So this kind of placing an atom here will actually, you will be able to excite it, not if you look at quadrupole interactions, but if you look at octupole interactions. Okay, what am I trying to say with quadrupole and octupole interaction? So if we go back to our basic quantum mechanics of interacting lights and field, we know, for example, we can calculate transition probabilities any way we want, but one of the ways to do it is through the Fermi-Golden rule. And the Fermi-Golden rule basically tells us, you have your initial state, you have your final state, and the transition probability between one and the other one is given by the matrix element of the interaction Hamiltonian between these two things. The interaction Hamiltonian, of course, you calculate it as the vector potential times P and the same thing inverted. And if you do that, you can do certain approximations for the field. The first approximation that you can do for the field is saying, okay, I will do what's called the electric dipole approximations. You can get to electric dipole approximations through many directions, but basically in the end, you end up with the electrical dipole approximation only retaining the amplitude of the field, the polarization of the field, and the fact that the field is oscillating. So the dipole approximation really it's saying I don't really care if you're a traveling wave, a Gaussian wave, or whatever wave, I only care about the polarization of the field. So in which direction is the E field pointing, and that the frequency it's turning on and off, and the amplitude that it's turning on and off. And if you do this approximation, you find out that the initial and final states are related by different rules that we know as the transition selection rules. And one of those rules tells us that the change in orbital angular momentum of the atom can be delta L equal to plus minus 1. So you can change from an S state to a P state, from a P state to a D state, from a D state to an F state, and so on. So if you look at, we will use calcium as our battle horse here and our experimental atom. So if you look at, for example, energy levels of ionized calcium, you have, for example, a ground S level. These dipole transitions, which are the strongest ones, are the ones that go from S to P, and from P to D, and from P to D, all of these ones that are the light ones here. But you have another special transition, which is this one from S to D. Here the change in orbital angular momentum is delta L equal to 2. This is not a dipole transition, this is what we know as a quadrupole transition. If we calculate the matrix element between an S and a D level with this field, we will get absolutely nothing. So what do we need to do? We need to go one order further in the expansion of our field to see what's the possibility of exciting there. And in doing so, we see, okay, the next order of expansion, of course, you will, whatever you have, whether it's a plane wave and you take the plane wave component, the fact that it's a traveling wave, whether it's a structured beam and you have some structure in some direction, your next term in your Taylor expansion will always have the coordinate. It will have the coordinate on some length scale. If it's the traveling wave, the length scale will be given by k. If not, it can be given by any other number. I'll show you about that in a second. But whenever the coordinate appears, you finally find that the difference between I and F can be delta equal to 2, and then basically you can do transitions between this level. And actually there's a very nice interesting thing, and a very nice interesting small videos that I'd like to show you in a discussion that I normally have when I teach atomic physics and I teach these things, which is, there's a curious thing that although one draws the orbitals in this way, one could ask oneself, okay, what's the dipole moment of this orbital? You have an orbital, another orbital, a distribution of charges, but in all of these cases, the dipole moment of all of this charge distribution is 0. And you have something that has no dipole moment, and you're putting an electric field, and somehow you're reducing transitions between one and the other one. What is actually happening here? Where is the dipole moment? When is the atom oscillating and absorbing and emitting photons? It's actually oscillating when it's emitting or absorbing photons when it's in a superposition of these two. So if you just do the very simple calculation of getting this orbital and calculating the superposition of this orbital with this orbital. Of course, they have different energies, so they will oscillate at different frequencies. And if you just calculate the very simple evolution of the Bohr with the Bohr frequencies of each two, you will see very easily, okay, this thing interacts constructively with this at some time and destructively with this at some other time. And at the given other time, it will go in the opposite direction. And that's what generates this oscillating charge that actually gives you a transition. And that's very... Podemos ver los primeros videos. Los que están en Chrome. These. So here you basically see what happens with the charge distribution as you go through a transition. This is a dipole transition. So that's if you're in the p state. At some point, you're in a superposition of both p and s state, and then as the state evolves more into the S state, it finally stops oscillating, and your charge, of course, stops oscillating, and that's why we know, or that's how we can explain modernly the Bohr ansatz that an atom only emits when it's changing level, or a charge only oscillates when it's emitting level, and when it's changing level, and not. Is that me? Is that? No, it's not. Anyhow. That's how we understand a dipole charge. You see a dipole charge basically, a dipole transition, so it's basically a charge which is moving in one direction or the other one, so we need a field that actually shapes this transition in one direction and the other one. What happens in a quadrupole transition? A quadrupole transition is a little bit more complicated, so you basically have to push in one direction and pull from the other direction, so it's not just a field in one direction, you need field in one direction and somehow a field in the opposite direction, so you need this kind of saddle horse saddle situations where the electric charge distribution is pulled in one direction and pushed in the other one, so you can actually transition from levels which are a level which is an S level directly non-stop onto something like a P level, a D level, sorry, which has that charge distribution. Okay, thank you. Where do we... Ahí no está pasando, ahí no está. No, este video ahí no. So, we are back. Perfect. Where do we get this gradients? Of course, in a traveling wave. A traveling wave, in a complex representation, we write it like that. And of course, this is a gradient in the direction that the beam is traveling. When we take the Taylor expansion of this, we see a constant term. This gives rise to the dipole interaction, and a linear term with a scaling factor k, z, that gives a gradient in the forward direction. But in the vortex beam, this rho quantity here, as I showed you, this is the vortex beam for L equal to 1, you have rho to the power of 1, that's a linear dependence of the coordinate, but now the linear dependence of the coordinate is in the transverse direction of the beam. So you actually have something that you have a field that's turning on in one direction and a gradient that's turning on in a different direction. And these things, both of these things can be used to drive quadrupole transitions, and both of these things can actually be used to give an atom more angular momentum than just one unit. So the first thing that we see, so what we did is we did an experiment where we were moving an ion across the beam and we measured the intensity, and we arranged the polarizations and the magnetic field in such a way that in the case where you see in red, so here you see the beam excitation as a function of the ion position across the beam for each of these beams, and there were two configurations that we could choose by changing polarization and magnetic field. One configuration in which the transition or the excitation would be sensitive to longitudinal fields, so to fields in this kind of fields in the z direction, and in the other case it would be sensitive, in the blue it would be sensitive to transverse field. And what we see, if you look at the Gaussian beam, of course, the Gaussian beam it goes, when you're sensitive to longitudinal fields, you just see the intensity of the beam, but if you look at the transverse field, which is in blue, you actually see that there's, as the beam turns off or goes dark at the side of the Gaussian, there's of course a transverse gradient, and you see this as to like a little ass on the ground there. The same thing happens, but much more surprisingly, for a donut beam. For the donut beam with L equal to 1, you see, of course, if you look at the longitudinal gradient, you see the two humps showing the intensity of the beam on one side and the other one. Actually, this quantity is not proportional to the intensity, but to the square root of the intensity, because what we're measuring is Rabi frequency. I will get that into a second. But more surprisingly, if we turn the polarization of the magnetic field in such a way that we are sensitive to the transverse gradient, we see the excitation that we see in blue, when you see this very interesting peak in the middle, where we have an ion that can get excited even when it's lying in the dark center of the beam. That's a pretty amazing result, that you can actually excite atoms in the dark. How do you do that? Well, you choose a transition that's actually not principally driven by the amplitude of the field, but by a gradient of the field, and you place the atom in a place where there's a big gradient and a small amplitude. Of course, there will always be some amplitude, because you're never positioned in an infinite place in space, you're always occupying some space, so your atom will feel at its sides that it's, as in the kids game, a little bit to one side than the other one. So what happens if you go to L equal to 2? Of course, L equals to 2, you don't have a gradient in the middle, so you're not sensitive to that, so you just see the gradients of these beams powering off and on to the sides. I didn't say it yesterday, and I'll say it today, though some people did interrupt me at some point during the talk. If you have any questions during the talk, raise your hand and ask me questions. Good. So this was a very, very first nice result. This is a little bit more detail of it. This was the result that we got in 2016. This was the prediction that we had made actually in 2012. I guess it's more annoying for you than for me because I'm on this side of the speakers. But and you actually see that there is a difference in shape. You see this shape is really like, it looks like when you take the absolute value of something, that's because it's Rabi frequency, and actually it has to look like that. And in this we were missing a square root. You know, sometimes you make mistakes, you publish mistakes, there they are, then you get time to correct them. So this is a picture of me, very happy. The first time I actually had these results, you see the results on the computer there in blue and in red, one on the other one. And I put this picture because I want to tell you three things about this result. First of all, this experiment we managed to get right the third time we tried it. The first time we tried it, yeah?
How many years total?
Sorry?
How many years total?
How many years gone in between?
Just 3 tries.
So the first try, you see this is from 2012. The first try was in 2011. So what was the first? This is horrible. I would even just shout and turn this whole thing off if you want. The first try was in 2011. And we had some parameters wrong. So that's the first result. Shut up and calculate. Sometimes you just have to calculate to know how to hit the right parameters. And that's how the first theoretical paper came with a proposal with the detail of what we have to do. The second experiment was down in 2014. We had some signal and we totally lost it. And we thought, it must have been just craziness. And then we, after a couple of months of searching what was wrong, we found out that one of the fibers that we used was burned in the inner facet, and that the polarization was drifting like crazy, so there was no way we were seeing what we wanted. And once we got that figured out, which we figured out when we said, like, let's drop this experiment and do something else, and we come back to it, we went to something else, and we said, like, oh, it's a polarization drifting. It's like, let's go back to it. And then it was 2015, I think, that we finally did a nice measurement. So all in all, 4 years. And so leave ideas to rest, and it's the optics. Many times when things don't work, it's just the optics, stupid. Just check your optics very well whenever you're doing experiments. So how does this experiment more or less work? So the experiment happens in a vacuum chamber with ultra-high vacuum where we have one single trapped ion. This ion is is trapped by a segmented foil trap. I will tell you in a second how all of this works. And we can move the ion sideways. The beam that we want to use as a spectroscopy beam is around 729 nanometers. We placed it through a structured faceplate that I told you yesterday. We could change the polarization of the beam through some wave plates, and then we would focus the beam close to the diffraction limit with an objective lens. And then we could observe the fluorescence of this ion with a couple of auxiliary beams that would excite them, and the fluorescence would be recorded by a very sensitive CCD camera, which is called EMCCD. But to let you know a little bit how this works, this is a visual tutorial of how ion trapping works. So, relax and enjoy. So what do you need to trap ions? So this is, as I said, very, Marcelo said this is a relaxed school. This is a relaxed version of how to trap ions. So the first thing you need is a trap. And ions are charged, but because of the Earnshaw theorem, there's no way we can generate a configuration of static potentials that can hold the traps in one position. So Wolfgang Paul came with a method which is pretty nice, which is he realized that if you have a configuration of electrons like this, doing a quadrupole, and you alternate in time the potential such that at a given time you have positive, positive, negative, negative, and at a subsequent time you have positive, positive, negative, negative, the charge will try to go in one direction or the other direction, one direction or the other direction, but in the end it will just somehow revolve around the center in a dynamic confinement. And this way you can generate what we call a pseudo potential that allows you to trap charged particles in space. So this video I forgot to give you. No, this video is not there. I bring this video tomorrow. So there's actually a mechanical analogy of this. So if you get a piece of wood or actually a real horse saddle and make it turn and you put a ball on it, of course, if it's not turning, the ball will fall, but if it's turning and it's turning at the right velocity, the ball will remain a long time at the center revolving, trying to fall in one direction, but the potential moving fast enough to catch it. So this is how a real trap works. So it looks, so it's a lot of pieces of metal which you connect from the outside through cables. This is all inside a vacuum chamber, which you need to, so this is another kind of trap. These are two traps. These are the two traps that we actually operate in Buenos Aires. It's a linear trap. Ions will be stored there in the middle. You have the oscillating potentials between these electrodes, a static potential in this direction. You can trap linear traps of ions in this direction. Just to give you a sense of size, this separation here is around 1 centimeter more or less. This is another trap that we work with. This is a very beautiful picture that a friend of mine did, where you don't see it from over there because of the resolution, but there's a very faint dot there. Those are trapped ions in the whole trap. The trap has a millimeter size hole, and there's some electrons coming from the top and the bottom. And so what do you need? You need a vacuum chamber. So you put these traps inside a pot, a metal pot with some windows so that you can also throw lasers in and look at the light. And you use pumping stations. You bake your chamber, so you heat it up so all of the water goes out, all of the dirt goes out for a week or two, and then you reach pressures which are in the ultra high vacuum, so below 10 to the 11 millibar, which is what you need if you want your atoms to be stable and not be kicked around by vacuum pressure. What's the next thing that you need? Of course, you have your trap, you have your beautiful vacuum, but you need to get your atoms there. So what do you need? You need some kind of way of delivering your atoms in there, and that's normally done by means of an oven. So if you look at, so this is a trap which is a structured trap. It's very good. That's it there. Atoms get trapped here. This is the trap that I showed you, and this is the other trap that I showed you. And if you look, all of these traps, so atoms come in different types. These three traps have the same kind of ovens. you can see that apart from the traps that look very different, there's something that you can see in all of the pictures. And it's the ovens. Who can tell what the ovens are? So in this one, the oven is this huge thing here. It's funny, you have a very small trap and then you have an oven, which is a huge thing. So this oven is just a piece of metal with a hole. You put granules of whatever you want to work with. This is connected to a tungsten rod to another electrode. You pass a current through this gets hot, and this emits a hot vapor gas. Here you see also the very delicate trap, the very delicate ions, and the oven, a canon. And here you also see your trap. This is the trapping region of your electrodes, and here from the bottom are the two ovens coming up. There are other ways of loading ions in traps, by ablation, by 2D mods and stuff, but in the end you need some kind of atom source. Good. Then what you need is we're working with ions, we're working with trap particles. Normally when you heat up a piece of material, the vapor that comes out is neutral, so you need some kind of ionizing method. And the old way of ionizing was through electron guns, so you basically had a piece of hot wire that you put on a potential that emitted electrons. Electrons hit your atoms, and every now and again they would hit an electron out of your atom and into the continuum, but that's very dirty because then you have all of your surfaces charged with any kind of electrons or other ions or whatever. And the modern way of doing it is through a process called resonance enhanced multi-photon ionization. So basically you have, this is the energy level for neutral calcium. So basically you do a more than one step process. This is a two-step process where you first excite one of your valence electrons from the ground state to an excited state in a resonant way, and then you excite it from there to the continuum, basically ejecting this electron out of your ion or your atom, which is turning into an ion. It's transitioning and becoming charged, and if you do that inside of the trap, and if you then shine some lasers that allow you to observe, so this is the energy level of the calcium ions, so the energy level of the calcium ions, as I showed you, has a ground S level that you can excite through a very short-lived transition of 7 nanoseconds, and this will absorb and emit photons all the time. That will allow you to observe the ions, but unfortunately, this atom has a decay channel to this state, which is a T3½ state, which has a very long lifetime. And if you don't take your population out of this, very soon your electron will end up here and your atom won't fluoresce for a second, and then later it will decay, but it takes a long time, so this is a very long lifetime. So basically what you do is you put an extra laser, which you call a repump laser, which allows you to repump the population back into the fluorescing cycle and allows you to scatter a lot of photons. With this process, you don't only observe your ions, but you can also cool them. You can cool them down to the Doppler limit through the Doppler process, which I won't get into describing in this talk, but if anybody is curious about how it works, we can talk about it in any break. For that, you need a couple of lasers, and acousto-optics, electro-optics, and plates to control turning off and on lasers, so your optical tables sometimes look like this. Now, in the last years, these things have started to compact a bit, and people have started to put these things on racks, but if you just look at what it looks like, this is a laser which is emitting, and it's going into these little buggers here, which are acousto-optic modulators, which allow you to turn on and off and to switch the frequency of lasers. And then normally lasers are coupled into fibers, which are, if you look at all of these cables running here, those are all optical fibers that are taking the light over to the experiment, which is somewhere else. So you bring up your light with your fiber to the experiments, and you see, for example, in this setup, you have, on one side, we had the photoionization lasers, which allows us to create the ions, and on the other side, the fluorescence of the observation lasers, and then the fluorescence of these ions gets imaged on the camera through a lens. And if you do everything well, you can trap first, for example, a cloud. This is a cloud of a couple of thousands of atoms, which are hot to a couple of Kelvin, all moving around. And if you tune your laser parameters so that they get colder and colder, at some point they crystallize. They go through a phase transition and they form what we call a Wigner or a Coulomb crystal. It's a crystal, just like crystals of atoms, but these ones are crystals of ions. So the main force is not like a Van der Waals force, but it's just a Coulomb force, so the shapes are a little bit different. So this is a crystal of 14 ions on a 3D trap. These are different kinds of ions, all taken in our lab. So this is a linear chain of ions, this is a smaller linear chain of ions. This is a linear chain of ions with one atom of another species here which doesn't fluoresce. All of the others are fluorescing, and these are different chains of ions on this other trap which has this structure with traps like pancakes. So depending on how you put your potentials, you can trap and you can do different funny things with the shapes and the organizations of your crystals. Now the last video. And if you have segmented traps, so you can actually put different voltages to different ions, you can actually, to different parts of your trap, you can actually, this is a video of what you can do. So this is two ions, that we can separate by putting the potential high in the middle of the two, or we can move them to one side or move them to the other side. So you can control the position of the ions very well along some of the dimensions, not along all of the dimensions, because of this fact that on one or two dimensions you can have a quasi-static potential, but on the other one you have this oscillating potential. But at least on one or two dimensions you can move your ions more or less freely like this. So this is what we actually did for moving the ion across the beam. We were moving not two, but one ion across the beam by changing the potentials around the trap. So I showed you, so I'm going back to orbital angular momentum, finishing this tutorial on how to trap atoms or ions. I'll go back to try and convince you how also what we saw was an evidence of the beams actually carrying orbital angular momentum. There's a question?
Maybe later.
Okay. So, a recap of the angular momentum of the beam. So what I showed you yesterday was if you just have polarization, so if you just look at the vector potential that looks like this, you have your polarization vector in the complex, written in the complex way. This accounts for what we all learned, like the photon has one unit of angular momentum, which is it has plus h bar or minus h bar, which allows you to change the mj number in plus minus 1 whenever you're in a configuration with rotational symmetry. And these are the kind of things that I talked about yesterday, the historical remarks of the observation of Hanle and Baer, and all of the discussion with Kastler and so on. Later, I showed you that if you put an extra e to the IL5 phase, the total angular momentum of the beam has actually a component that has to do with the intrinsic spin angular momentum, and it can be plus minus h, but there's another quantity which can be plus L h bar, and L can take any integer number, positive or negative, and that's what we know as orbital angular momentum. So the question we ask ourselves is, can we actually see changes in the atomic transitions of mj equal to plus minus 1 plus whatever L we put into it? And how do we see this on an atom? Well, let's look at the quadrupole transition, which is the one that I showed you that one can get excited through at the center of these beams through and let's look at it in more detail. So if we put a magnetic field, the S level, which is an S1/2 level, splits into two states, one with plus 1/2 and the other one with minus 1/2 spin. And the D5/2 level, so it's the D5/2 level has these 6 magnetic states. And if you just have polarization, so if you're in a Gaussian beam and your atom is in the center of the beam, like my laser pointer, or less is where you are in the center of the beam, and your magnetic field is in the same direction of your beam propagation, you have rotational symmetry. So the only transitions you can make are delta L equal to +1 going from, so if you start from an electron which is in this state in the ms minus 1/2, you can either go to +1/2 or you can go to -3/2. So you can, I'm coloring the spin angular momentum in yellow for +1 and in blue for -1. So you can only do these transitions and all of the other transitions are basically off. If you try to probe any of the other transitions, you will see that you cannot excite. You tune your laser to one transition or the other one or the other one, you see them not occurring. So what do we expect? We expect that if we add the orbital angular momentum, so the orbital angular momentum can be -1, 0, or +1, and we can combine it with the spin angular momentum in any kind of way, we should be able to explore all of these transitions. So if we start in the -1/2 state, we should be able to go to the -5/2 state, and we have the combination of minus and minus, or if we have counter-rotating spin and orbital angular momentum in any of the directions, we should be able to do the delta N equal to 0 transition, and so on and so forth. So what did we do? We did exactly this experiment. We set a laser to each of these transitions, and we probed the excitation strength of these transitions, and we did it for all of the possible combinations of the angular momentum of the photon. How do we do this? How does this experiment happen? We first prepare one of these states, and that is done through a process called optical pumping. Then when we prepare the first state, we turn on this beam that will excite it. It's tuned to one of these transitions. It will excite the beam. We can, of course, move the beam with respect to the ion, but these experiments that I'm going to show you now are with the beam in the center. The ones that I showed you before, you could displace it like it's here. For the ones that come now, they're not displaced. And then afterwards, so you could have, if you were tuned to the transition, that the transition is allowed, you would have gone into this state. And if you didn't go to that state, you will stay here. So afterwards, you turn on these two beams and you observe fluorescence. If you make the transition to this state, your ion will be dark. If you didn't make the transition, your ion will be bright. So you measure bright and dark probability to account for the probability that the ion actually made this transition. And actually the ion will make rapid oscillations between these two states, creating a superposition of them too, and what we measure is how fast these oscillations move the population from one side to the other. So this is what we do. So again, the sequence does first Doppler cooling and optical pumping. Then we have our pulse probe, our probe pulse, in the transition that we want, tuned to one of the sublevels, and then we do the detection. And as we change the time of the probe pulse, we see the population going. So we start on a dark state, a bright state, so we start here, so this state is bright. Then as the interaction time is long enough to move the population completely from here to here, we turn to a dark state, and then again to bright, dark, bright, dark, bright. This is if a transition is on. If a transition is slightly on, the frequency of oscillation is lower. If a transition is totally off, the frequency of oscillation is almost nothing. So this frequency of oscillation, which is the Rabi frequency, is our measure of the intensity of the transition. And this is what we show in this plot. So we tune the laser to the -2m transition, to the -1, to the 0, to the 1, to the 2. So we probe all of the different atomic transitions, and for each of these atomic transitions, we try all of the different combinations of the photon angular momentum, whether it's -2 in total, -1, 0, 1, or 2. And what do we see? The Rabi frequency is always much, much bigger when the content of angular momentum of the photon matches the change in angular momentum of the atom. So 2 and -2, 1 and -1, so the diagonal here, right? You see, the diagonal is much, much stronger than the out of the diagonal element, showing that two things. First of all, you can do this transition. So these transitions which would not be allowed, this one's in the middle, which would not be allowed, are actually allowed. They're weaker than these ones here, but they are still there. And they're much stronger than any other thing. These other things here, which are not totally off, can be accounted for different spurious effects, in particular the fact that the ion is not perfectly positioned at the center of the trap, but it's a wave packet that would have some spread, and also due to the purity of the polarization of the beam that we have. So basically what this tells us is, okay, a photon can actually have more than one unit of angular momentum. It can have 2, 3, or whatever you want, and you have to combine the orbital and the angular and the intrinsic angular momentum to account for all of the angular momentum that the photon has, and that it can actually transfer to an atom when exciting an electronic transition. So we can then happily close this box here, saying, okay, we saw in atomic spectroscopy the influence of orbital angular momentum, so we can actually transfer orbital angular momentum from a beam to the electron, to the valence electron of an atom. Tomorrow we will go through something that's a little bit in the middle between these two. But before I do that, let me tell you something that actually also got us scratching our heads for a long while, which is the following, which is when we published this paper, we understood pretty well everything in this plot, but not the height of this bar. The height of this bar we could not account from the theory that we had, which was basically very simple theory of how a transverse paraxial beam looks when you focus it onto an atom, and the difference intensity on one and the other ones are just the Clebsch-Gordon coefficients that you get from that, and there's not much to it. But the intensity of this one was wrong, and it was very badly wrong. So now what you will see in the next blocks is just the values of the diagonal here. When you start from the n-1/2, so this is the values that you are seeing, this is the experimental values, the dots here. And this is when you start from the other state. I didn't show it, but yeah. So those experiments that I was showing are starting from the -1/2, of course, we also just for completeness also measured everything from the other one, but it's just everything like a mirror reflection. And you see the theory that we had, where the light bars here, which is, you see fixed, it's going very well for everything, but not for the interaction here. So we were expecting an interaction which was almost 3 times smaller. And we couldn't get our heads into what it was until a year later, we're talking to a collaborator at the University of Buenos Aires, and he said like, hey, look, I was like scanning through one of his papers where he was studying the effect of structured light, not on atoms, but on semiconductor surfaces, and I saw that there was a special factor appearing when orbital angular momentum and spin angular momentum were counter-rotating. And this goes back to what I was telling you yesterday about non-paraxial effects. So we have the spin angular momentum, which can be plus or minus 1. We have the orbital angular momentum, which in our case could be 0 or plus minus 1. Of course, it can be other stuff. And the thing that happens is that when you have parallel L and sigma, if you look at so this is how a cut of the beam looks at a given moment, and this is how the polarization vector looks at a given moment. And if you just calculate what happens with these vectors as you focus them, you see that the transverse component of what you have in the y cut with respect to the x cut have equal and opposite faces all the time. So the transverse component always, the longitudinal component always eliminates. It interferes destructively because you always have a positive part and a negative part. But in the case where they are anti-parallel, so when you have spin polarization in one direction and orbital angular momentum in the other direction, these two contributions add up. And they add up to a longitudinal field, which is even bigger than the transverse effect that we were seeing. And that accounts for the theory, which is a dark orange here, which match very, very well the results. So also another lesson that I learned here, like letting things rest, is like, look at this. Let's keep on asking people if they saw something like this, if they have an idea on how you would solve this. And sometimes, so actually when we published it, we just said like, okay, let's publish it and let's see if somebody finds it and discovers what it is. It's funny that actually sometime later also, somebody that hadn't seen our paper, this paper from 1 year later, when we explained this effect, came to us and told us like, hey, I have a theory that actually explains all of your intensities very well and so. And of course it accounted for the non-paraxial effect of the beam, which was kind of nice. So, part 3, this is a little bit the last part of part 5, sorry. The last part of today, optical activity. So this is a part where also it has to do with a little bit how I got into this subject and how I was a little bit out of motivation for quite a while because of things that I had seen published. But I was happy that people actually published a lot of negative results in this respect. So it's about this little part here, and it's like, okay, the question is, can the orbital angular momentum of light change when it interacts with matter? Can, the same way as the polarization can rotate when you go through a material that is that doesn't have mirror symmetry, and we call that optical activity. Can you have an optical activity but with the structure of the beam? And for a long time, it was believed that this was not possible. And many people, well, actually, people just first believed it could be possible, and there were many negative results. Okay, there you go. These were 3 papers that some of them had titles that were suggestive of the negative results, and some of them not. So this was said interactions of twisted light with chiral molecules and experimental investigation with negative results. So basically nothing, but elegantly put. Circular dichroism of cholesteric polymers and the orbital angular momentum of light, where nothing happens. Which is nice that these people publish this result, you know? They're basically saying like, to this amount of percentage of error, we see nothing. And this one, which was a little bit, they were a little bit more brave in putting the title, Negative Experimental Evidence for Magneto-Optical Dichroism. So with this thing in hand, it was like, somehow the community was at the time where we were doing this experiment saying, you'll see nothing on atoms. The structure of the beam is enormous, atomic transitions are given by things that are scaled by the size of an atom, you'll see nothing. Fortunately, as I showed you, there was something interesting to see on the quadrupole transitions, and I'll show you tomorrow also other things that are interesting also on the dipole transitions, as we even learned later. But even though this thing gave me negative results, I'm very happy to tell you that in the last years, not so long ago, this paper is from 2016, this is at the same time that our paper came out, actually, more or less, but I only knew about this paper much later. People observe optical activity, so they shone light with a given amount of orbital angular momentum on a sample, and they would see what was the emitted light, if it changed the orbital angular momentum or not, and they would see what was the absorption for different values of optical angular momentum, and they basically saw that if they had the same kind of very big complex molecule in the left-hand side version or in the right-hand side version, that's our red curves or right curves, you would see an asymmetry in this helical dichroism, which is basically how much of the light that comes in and out changes. So the thing is, what they change here is that, look at this mess here. What is this mess here? What is this drawing? So, so this drawing is a drawing of how it says here, unique nanoparticle aggregates. So they basically had these molecules, which are right-hand side and left-hand side, and they mixed it with nanoparticles, so the molecules would arrange the nanoparticles, so would couple to the nanoparticles and create these big structures, which were of the size of the focus beam, which were right-handed or left-handed structures, and effectively being able to change at a dipole interaction level the angular momentum of the beam. But the critical thing here is that the structures are big. So this, although they're nanoparticle, they're more like almost micron-sized conglomerate of stuff. So the constituents are nanoparticles, but the whole thing on which you shine is actually thing that's structurally left or right in a micro-size scale. And actually, a little bit later, in 2020, some people developed this very funny materials. So, oh, the length scale is missing here. I don't know what happened with it. I think this is 500 nanometers. I can't remember what. We can look for it. If somebody wants to search for that quickly and look for it. If not, never mind. It's the size, more or less the size of the wavelength, and they're focusing light on this, and what they basically see is the scattering intensity, and they see that the scattering intensity changes for the right-hand side version and with respect to the left-hand side version, depending on the orbital angular momentum of the beam that's impinging. So you see what they do here, they actually change the orbital angular momentum of the beam from 0 to 70. The way they do this is with spatial light modulators, where they can change very easily the orbital angular momentum, and they change it from, you would say, from 70 down to 0 and then up to minus 70. And you see that the one that's plus, in this case, scatters a lot, and in the case where the structure has the other direction, the one that's minus scatters a lot. And I looked at all of this and I thought to myself, like, this is all very nice, but we actually have, you know, if you're saying like, oh, scattering or absorption or whatever, changing the structure of light while scattering through matter, we actually had that. We knew that from the very beginning. Our spiral plates are exactly that. All of what I discussed on how to change change a beam from a Gaussian to a beam with orbital angular momentum, all of the discussion of yesterday at the end of how would you a fork type of hologram or a plate that has a spiral phase plate is a dichroic element for structured beams. So yeah, in the end, sometimes it takes a long road to discover that you were always at home. I never realized I was going to do a citation at the end of this talk. This is another example, and this is what I just said. So, if you want to see a very nice review about this kind of things and about orbital optical activity, I recommend you this paper by Ken Forbes and David Andrews, which is very nice. It's very recent, or 4 years ago, and it covers all of this old experiments, new experiments, and the search for optical activity. Good. So in the end, this was a tick all the time. We always did this, was there since the beginning, but we didn't realize it. And as I said, we will study a little bit of an interplay between these two things with atoms tomorrow. So now to finish, I will, let's finish here. I will put this on tomorrow. Thank you very much.
Thank you, Christian. Questions? Yes.
Christian, so you have shown that now we have the selection rules in the case where we have the angular momentum, so we can add another L. But you show for your measurement when you move the ion, and then the scatter matrix when you have it in the center of the loop. So does the quadruple selection rules now have a dependence on the place that you are? Is it beyond the polarization?
Yes, it does. The selection rules, as they are, like the strict selection rules of the conservation of orbit and angular or of angular momentum along one direction, only applies when you have rotational symmetry. And if your ion is not placed at the center of the beam, it doesn't have rotational symmetry anymore. So then at that point, you can actually start to have other transitions. And actually, normally the way, and we'll go back to that. So, people have been working on quadruple transitions for a long time. And using only spin angular momentum, all of these transitions, this one, and this one, have been done. And you can do that. But how do you do that? You basically break the rotational symmetry, but by making the direction of propagation of your field and your magnetic field not be collinear. So if your quantization axis of the field, which is given by, or the easiest quantization axis of the field, which is given by the propagation direction, matches the one of the magnetic field, which sets the magnetic quantization axis of the atom, you have this strict relationship. If not, not. And that's the same thing that happens in dipole transitions. So in dipole transitions, you only have sigma plus or sigma minus if B and K are collinear, and you have pi when they're not. So, same thing here.
Thanks.
Hi, thank you. I think I was asking something very similar to this, in the sense of what is interesting about, because usually the dipole coupling is stronger than dipole, but what is the interesting thing about making Rabi transitions with quadrupole and not with dipole?
Good. So it's normally very difficult actually to make Rabi oscillations on dipole transitions. Because in order to see Rabi oscillations, in order to control coherently your population or your atomic state, you need a couple of conditions to be met, but one of them is that your Rabi frequency is much bigger. Your Rabi frequency and your switching times, the times that you can turn off and on signals, have to be faster than your decoherence times. And in typical, there we go. In typical dipole transitions, the lifetime that you have is around 10 nanoseconds. 10 nanoseconds is at the limit of what you can do electronic turning off and on of any signal, radio frequency, radio waves, whatever. And yeah, that may be. And on top, it's at the limit of the Rabi frequency that you can actually do. You can do Rabi oscillations on dipole transitions. You can do it with pulse lasers, like femtoseconds pulse lasers. So you can do Rabi oscillations on dipole transitions, but it's difficult. So it's much easier to do Rabi oscillations to see coherence effects when your coherence time, which here are dictated mainly by the decay time, are much longer than any time that you can control. And quadruple transitions like this one normally have lifetimes or decay times in the order of the second, of the millisecond. So this one is nicely long. There are sometimes some that are longer, like some that are years long, but they're much longer than switching times that you can have for a laser, which are microseconds, milliseconds, whatever, tens of nanoseconds. Hundreds of nanoseconds is not really. So that's why quadruple transitions are interesting, because being not allowed, they're also much more disconnected with the environment, so they're better to do quantum business.
So the Rabi frequency of quadruple transitions is larger than dipole?
No.
The other
It's
thing.
smaller. So you need more laser power.
Okay. So it's good to have smaller Rabi frequencies.
So you want to have, no, it's good to have longer decay times, longer decoherence times, and then you want to put your Rabi frequency above your decay frequency. Yeah? So here your decay frequency is 1 hertz. You want your Rabi frequency to be way bigger than 1 hertz. If you can get it to the kilohertz, if you can get it to the megahertz, you're doing very good. And that's normally what you get there. Of course, your Rabi frequencies here can be much faster. You can have terahertz if you put enough, but the thing is, it's very difficult to see, like, to turn on and off a laser in below 1 nanosecond. So it's difficult to control things at that time scale. That's why dipole transitions are difficult to run coherent physics.
Thank you.
More questions?
Hi, thank you for the lecture. My question is, it's possible to study some entanglement in this kind of experiment? Just
Yes, the question is entanglement between what and what? Light and
between
matter?
this photon that is emitted and some other.
Good. So it's very difficult.
Yeah, because I already seen like a billion atoms, ion traps that made something like that. But I don't know if it's the same thing that you're talking.
So we consider and analyze the possibility of. So there's people working on atom-light interfaces where your atom emits a photon and that photon has information either in its polarization or in its time information about the atom, and you use this as a repeater and you want the atom and the photon to be entangled. You could in principle do that also with a quadrupole transition, also with the orbital angular momentum, but it's just kind of inefficient and it's difficult. You could in principle, there's nothing that tells you not. But normally, for example, for this kind of atom-light entanglement schemes, you end up using a decay through a fast channel, through a dipole channel. And there's not so much information about the structure of the light. Because the decay through a slow channel, whereas that you have the structure information, is slow. It's not the best. But though on another direction, and we'll talk a little bit about that tomorrow, this kind of things, when you use them as optical forces, can be used to entangle atoms one with respect to the other.
Okay, thank you.
Hi, thank you for the lecture on this. I would like to ask you about the difference between the Laguerre-Gaussian beam and vortex beam.
I use vortex as I would say vortex is a general denomination of a beam that has a spiral phase. There are different kinds of vortex or spiral beams. There's the Laguerre-Gaussian beams, and there's, for example, the Bessel beams. Bessel beams are qualitatively different in the fact that they're not a solution of the Paraty equation, they're a solution of the full Helmholtz equation. The problem, they have good things and bad things. One of the good things is that it's a complete solution and it gives you all of the non-paraction effects, they're all in there in the Bessel beams. The bad thing about the Bessel beams is the same thing that's bad with plane waves, which is they have infinite energy, they propagate infinite into. So a Bessel beam, a Laguerre-Gaussian beam is a beam that turns off into infinity, it's like somehow well behaved. And a Bessel beam has, the same way as a plane wave, infinite energy. So they have difficulties in theoretical treatment, but most of them are good descriptions for, in a given realm, any of them are good descriptions for any physics that you want to do.
Thank you.
And one final question here.
Christian, so if you can use the quadrupole coupling to have longer coherence times, do you think that with your clouds, could you have longer, let's suppose that you want to use to make a memory? So could you have like bigger lifetime memories for atomic systems using the quadrupole couplings?
So yes, actually quadrupole and magnetic dipole transitions are the ones that are used for atomic memories in that sense. Or atomic qubits, atomic quantum registers are always placed or are chosen in such a way that that you have long lifetimes. So, for example, in the calcium system, there are two very popular qubits. One very popular qubit is what's called the magnetic state, which is, so this state, as I said, it splits into two states where you put a magnetic field, and those two are separated by a couple of megahertz, depending on the magnetic field. Those can be used as a qubit. Other people, and those are called the magnetic qubit. Other people use what they call the optical qubit, which is one level in this state and one level in this state. And if you have, moreover, if you have, so this atom, this is calcium-40, it doesn't have magnetic structure, but if you have a nucleus with a spin, then that also generates more levels, and you can have magnetic levels which are even sensitive to magnetic perturbations, and that are used a lot. So, yes, always when you want to do quantum Schmanzum on atoms, you choose downlink states.
So let's thank Christian again.